Welcome everybody to the Red Hat Research Days talk. Today, Renato Mancuso, who's a assistant professor at Boston University, will be speaking to us about whether we can control time. Really interesting topic. He's an expert on real-time systems, embedded systems, and a longtime collaborator with Red Hat and Boston University projects. And with us today also is Ahmed Sanallah, who is a senior engineer at Red Hat. He is also a longtime collaborator with several Boston University people. His interests are hardware and open hardware in particular, FPGA development, and of course, all the applications that you can use FPGAs for in cloud systems. So we're very happy to have both of them. Hope you enjoy the conversation. Feel free to jump in at any time if you want to ask a question. You can share your audio and video through Hopin, or you can type questions into the chat and follow up with audio video. So with that, I'll hand it over to Renato and Ahmed. Thank you.
Thank you, Heidi. Just a couple of things before we begin. So today's talk is not going to be a continuous presentation. We're going to have some pauses, which is a good opportunity to ask questions. So during the presentation itself, if you have questions, please put them in the chat, and I will do my best to relay them, just in the interest of time. But of course, at the end of the talk, we will cycle around to any questions that we couldn't get to, and I would actually encourage you to join us here on stage, share your audio, video, and ask your questions, take part in a discussion on what we talked about. So before I hand it over to Renato, just some context to the discussion. So over the past few years, we've seen the complexity of computing systems just skyrocket, whether it's multi-core systems in the cloud or multi-accelerator systems at the edge and cyber-physical world. And a lot of this complexity has been dictated by the requirements and the rising demand for data-heavy workloads. But here's the thing, nothing comes for free. And so the big question is, when we've made this transition from single core to massively parallel, what have we lost? And more importantly, with the tools that we have today in modern computing, is there a way that we can get back some of the control of the behavior of these systems? So to talk about these things, let me throw it over to Renato.
Sounds good. I hope everybody can hear me loud and clear. And first of all, I want to say thanks to Heidi and Hamed for the wonderful introduction. It's an honor to be here and to share a lot of the research results that we have accomplished with the help of Red Hat, but also with the help of a lot of the students in my group. So I owe this to them. So first thing I want to say is I'm sorry to disappoint any wannabe time traveler here. We're going to talk about control over application runtime. And so let's start diving right into and really talk about what is the problem at hand. At least let's put in some definitions. So the first thing I want to talk about is execution time. Right, execution time essentially is a random variable, right? As such, we cannot talk about the random variable execution time as just one number for our application, but rather in fairly complex systems like the one that Hamed referred to, we should talk about really a distribution of execution time. So we don't really know the shape. We can only speculate that certain shapes hold, but we can just talk about a generic distribution of execution time where on the x-axis we'll have, the outcome of this random variable, how long the application takes to execute, and on the y-axis is perhaps how likely is this to happen. And then if we were to be, superhuman beings and know about this distribution exactly, then we'll be able to say, well, there's definitely a best case, the shortest possible amount of time the application can run for. There is somewhere a mass of this distribution, the center of mass of the distribution, which is somehow what we typically care about in traditional computing, at least, which is the average execution time. And then there's something that we call, especially in the real-time community, something we deeply care about, which is the worst case execution time. So then if we understand the execution time follows some distribution, typically a noun, then we can try to define the concept of timeliness as the ability to essentially meet a constraint. And how we can define this constraint? Well, it's going to be a constraint on the probability that the execution time of the application under analysis is going to respect some threshold, let's say capital T. And we want that probability to be above a certain paranoia level, right? Called it 1 minus alpha. And then now it's super easy to talk about different domains. We can say, well, in real time, what we want is really a constraint on the WCT. Is the worst possible case. Assume that, for our system, it's always Monday. So the worst can possibly happen, which means our probability has to be greater or equal than 1, aka has to be equal to 1. But, nowadays, timeliness constraints are seeping their way into more, enterprise and cloud system, in which case we typically talk about 99 percentile latency, where the only difference here is that we are happy with just capturing, for example, 99% of the area of this distribution that is depicted on the left. What I want to mention here is that essentially when we talk about real-time constraint versus tail latency constraints, for example, we are really talking about the same object, and it boils down to our ability to control the shape or perhaps the center point of this distribution. All right, with this out of the way, what really means, right, and what is the importance of being able to maintain timeliness constraints. And, I'm a real-time person, so I like to make examples that fall in my field of expertise, but I welcome you to map what I'm talking about to your own domain. For example, talk about SLAs. What does it mean to keep or violate SLAs? But here, let's talk about a car. And typically, all of you have a car, which I hope has a so-called airbag control unit. This could be a standalone component or be integrated in a more complex SoC that runs other functions. But let's say it's a standalone unit. Well, then what this unit is performing all the time is essentially the same, asking the same question over and over again, right? So you can depict that kind of asking the question over and over again as a periodic activation, right? This is typically how we model a real-time workload. And each of these activations, right, asks essentially, perform essentially three things. First, it wonders whether or not, well, it collects a bunch of information. It wonders whether or not there's been a crash. And if there's been a crash, essentially actuates the airbag to make sure that, the passenger is at least having a soft landing. So what's important to understand is that here, if this deadline constraint is met, then upon a crash, the behavior of the system is as follows, right? As you approach the steering wheel, the airbag explodes and you have the soft landing that we desire. At the same time, if the behavior of the system on the temporal level, not the logical level, at the temporal level is wrong, which means that we overrun this deadline, then the behavior of the physical system is very different, where the airbag doesn't deploy and then you fly off the windshield. Even worse, if the deployment is late, now the airbag blows up in your face, which is double damage in general system. So the car that you want is the one where your airbag control unit will meet their deadline. Otherwise, bad things happen. And so this seems like a very constructed example. So if we look at the reasons why deadline violation or violation of timeliness constraints are becoming an increasingly more concerning problem, is that there are essentially two big trends in the industry that are pretty much colliding. And the first trend, I believe, aka a challenge, a trend that becomes a challenge, is the ability to integrate a lot of different functionality in a few control units or in a few big systems while preserving their runtime. So essentially right now there is a push in saying what was before something that was running on a dedicated machine. Here, really think about, for example, a single tenant VM in the cloud domain or a PLC in assembly plants or industrial plants, a microcontroller in a generic system, or an ECU if you talk about cars. And really, before we adopted something that we call a federated architecture, where we have a lot of this, each of them with their own dedicated resources. But now we realize that, well, this is not really efficient in terms of cost, power consumption, perhaps logistics of integration, maintenance, and so on and so forth. And so what we're saying is, well, perhaps we can integrate all this function into a few, maybe one, but in general, a few bigger systems and more capable systems. And then we are raising our expectation, right? Because we want that system to be able to handle increasingly higher degree of, for example, diagnostic and control, or being able to handle increasingly high bandwidth input streams, also perform cooperation with other systems of the same type, perhaps via data exchanges locally or globally, and then control the function of complex actuators potentially. And so if everything works, then it's great. We have self-driving cars. But at the same time, the problem with these two conflicting objectives is creating this friction where we want to have fancy new systems where if they fail, we have a huge cost. What is a recent example of this? Well, perhaps you heard the news of Tesla cars being unable to stop on time when there is kid-sized mannequins on the road. And once again, right, we observe a failure and we can perhaps only speculate that this is not a problem with object detection per se, but rather with the timeliness of the system that is supposed to detect an object in a timely manner and then react, so activate the brakes fast enough. We can only speculate until the CEO of this company goes in and tweets things of the type, well, you remember that crash, but now guess what? We have reduced the latency for object detection to actuation by 10%, pick a number. This is something that we can't really measure. So whatever this person says, we take it for granted, I guess. But we can only speculate that the problem was not in the logic per se, but rather in the timeliness of the system. And, perhaps we should start to get used to this kind of news, or perhaps we should work to ensure that timeliness in our system can be guaranteed by design, as opposed to following, a build and fix, maybe build, crash, and fix protocol. So with this in mind, right, let's a little bit go back and figure out what went wrong as we take our systems, start to integrate, and in doing so, increase the complexity of our system. So the typical approach in which we computer scientists, computer engineers have approached complexity has been by doing one very simple thing, which is introduce abstraction layers. So in other words, we typically take our hardware and then we want to forget as soon as possible that that hardware exists, abstract away and create a nice interface that can allow us to think about the hardware as a bunch of functional blocks, perhaps. And then we do that one more time. And then we create another software, for example, to be the abstraction layer as seen by the OS. And then create one more layer of abstraction from the OS to the application. And then perhaps we don't want to even run a compiled application anymore, but rather have interpreted languages. And so introduce more and more layers of abstractions. This is great to dominate complexity as being the way of doing things if we want to build our systems to be increasingly more complex. But at the same time, this approach fundamentally breaks down when we try to answer at least two classes of questions that my research cares about. One of them, perhaps is obvious from this talk so far, whether or not the system is timely. If the moment we forget what's really going on at the lowest level, immediately becomes much harder to reason about the timeliness of the system. And of course, you can already guess that the other class of questions that we are unable to answer efficiently become whether or not the system is secure. Typically, vulnerability seeps in the cracks of these abstraction layers. And if you start ignoring what's really under the hood, then guaranteeing any confidentiality or integrity, providing any integrity guarantees becomes increasingly hard. So what other class of questions fall in this domain? Things like power consumption of the system easily fits into this description. But let's focus on one class of question, which is timeliness, which is the big concern of at least the work that we do in my group. And so what I postulate is that in order to be able to try and dominate complexity while enforcing timeliness, we really have to pierce through these abstraction layers and understand what's happening under the hood. And then we can build methods, techniques to try and dominate timeliness and complexity at the same time. So one thing that I want to stress one more time is how we lose track of these details of this of the timeliness, the knowledge of how the system is behavior, just by raising the complexity of the system. And here I'm going to have two examples. A very simple system, call it a dumb light bulb, which does nothing but turn on a light when there is enough energy stored in the battery. So here you can see that if this is powered by a microcontroller, it doesn't need to have very complex logic. As such, the internal state, the internal possible behavior of the system is or can be fully known offline. And that means that we can really dominate the knowledge of this system, even at design time. So we don't need a fancy analysis method to understand how the system will behave, because essentially we can dominate the entire complexity space of this system. And by doing that, right, by using very simple systems, what we can achieve at a cost efficiently is predictability, because we know exactly how the system is going to behave, and we can embed that knowledge at design time and be confident that the system will behave in a timely manner once deployed. So predictability is not the only thing that you gain, is also the ability to easily analyze the system from a debugging perspective or from a behavioral perspective if you're trying to perform, for example, certification. Now, come 2022, and the same system in terms of functionality, perhaps, a light bulb, is faced with increasingly high expectation on what we want from this system. You can enumerate what this could be. It could be, having an interface to turn on only if the luminosity of the environment is sufficiently low, or maybe I have a voice-activated interface, or perhaps detect motion, communicate with other light bulbs in the same room or in the same building, have a fancy touchscreen interface, or be able to also interface with other sensors like temperature, you name it, right? The moment we raise the expectation on the system, what we are essentially pushing is an exponential increase in the complexity of the internal interaction between the software components, but also the hardware components that we need just to be able to accomplish the now expanded mission of the system. Why we're doing this in the first place? Well, we want context awareness. We want the system to be able to be, smart, quote unquote, so be able to understand the environment and react accordingly. So in other words, observe the physical world and make informed decision about where it is and how it's interacting with, for example, human beings, among other things. So really, there is a tension between achieving context awareness and, by doing that, increasing the complexity of the system, and then losing track of exact knowledge of what the system performs under the hood. And just to have a nice, a play of words here, I refer to system knowledge, so a system knowing itself, as a notion of self-awareness. So we have really a tension between self-awareness and context awareness. Somebody hopped in, so I don't know if they have some question at this point, but if you do, speak up if you want. Okay, so in this battle to go from complex systems where we have lost completely self-awareness toward a system where we dominate its complexity, but at the same time we know what's going on in the system so we can control and plan and act accordingly, where are we in our quest? Well, I would say the typical RTOSs are adopting a little bit what I like to call goldfish computing model, right? Semi-seriously here. But really, if you think about it, all we do with our applications is treat them as a global binary, throw them into execution, forget that we ever saw them once they complete execution, rinse and repeat. Yes, I mean, sometimes we could acquire some information about the runtime, but fundamentally what we ignore is all the fine-grained interaction between that application and the entire plethora of system resources that this application ever interacts with. That means cache, memory, I'm talking about memory buses, but also main memory, I/O devices, you name it. Okay, so what can we do? What needs to be done?
Sorry, not to
Yes.
I have a quick question.
Yeah.
It's a quick question just before you move on. I'm just curious. So you mentioned the importance of timeliness. What do you think is the relationship between timeliness and redundancy? Because if you're missing deadlines because the system is busy somewhere else handling some external disturbance, then redundancy could help there. Or do you think this is some inherent limitation of how we process data, so redundancy is not going to help us here?
Let me expand that and just say that redundancy as one way of doing over provisioning is always a solution. You can always solve problems with timeliness by adding more hardware to your system. This could be in the form of vertical or horizontal scaling. You can, if you can triple the frequency of all your components in your system, absolutely you can dominate timeliness, at least for the workload at hand. There are two things, though. Typically, this is expensive, and there is a reason why we are going from so-called federated architecture, where essentially you replicate your hardware n times and make sure that each of them handles a very small and contained subset of function into a few systems that can handle a lot of the workload. And the reason being cost for the most part, but also things like wiring, which still brings down the cost. Efficiency in power consumption, or things like business logistics. Just being able to deal with one supplier as opposed to 100 simplifies a lot of the engineering cost to get a system up and running. And things like upgradability, security also comes into the place where it's been demonstrated that really oftentimes the vulnerability in terms of security vulnerability are at the interface between systems that are working according to different principles and not well understood interactions between them. So again, over provisioning is a solution until the time when expectation from our system rises and then you're faced with, again, a workload that saturates your system. So eventually, what I'm predicating is not to try to make our hardware better, but rather, given an hardware that needs to satisfy high expectation on the compute workload, how do we manage things so that what's really crucial has a chance to run on time, and what's not crucial is prioritized less from a timeliness perspective? Does that answer the question?
Yeah, no, that makes sense. No. Just before you resume, just to the folks listening in, what Jen says, post your questions at any point. You don't have to wait for the pause. And we're going to typically try to pause on this timeline screen. So try to make sure your questions are in the chat before that, and I will do my best to relay them. So sorry not to.
Sounds good. All right. So again, here, I want to be a little bit inflammatory by saying that, well, our typical approach has been what I call goldfish computing. So how can we do better? How can we recover knowledge of our system and use it to our advantage? Well, in order to understand this, let's figure out where the bodies are buried here. So normally, the problem that we have is a problem of integration. So typically, if you buy a machine, you buy into a system capacity. So perhaps instructions per second that the manufacturer advertises, some notion of maximum throughput. And so what you would expect is that as you take workload in isolation and start to throw in composite inside your system, then every piece fits in nicely such that in the end, you can utilize the full capacity and everything composes or behaves altogether as if it was behaving in isolation. But the harsh reality is that actually what happens is that when you start integrating components into your system, maybe the first component when it's alone behaves as if, as just in the way you tested it in isolation. But then as you start integrating more and more components, what you see is essentially a temporal coupling between the different pieces that you keep integrating. And the more you integrate components, the more this coupling can become severe, sometimes degrading the performance of all the components involved if there is no careful management at the level of at the lower level of the system. Maybe let's put some number to this. So let's try to quantify what we define as temporal coupling or temporal interference. Typically, the way we refer to this is the presence of temporal interference as lack of temporal isolation. So here, we run an experiment on one of the brand new Intel CPUs. It has 32 CPUs on one single socket. And what we do is we observe one task in isolation at the beginning. And this task is memory intensive. So we're calculating how much bandwidth is able to extract from the memory subsystem. And then what we do is, and so this is the point at 1. So there's only one core active on the x-axis at the beginning. And then on the y-axis, we measure how much bandwidth in gigabyte per second is able to extract from the memory subsystem. So at the beginning, we are nearing 8 gigabytes per second, pretty typical for this kind of systems. Some people would say 8, 10 is a reasonable range for single core performance on these systems. And so what happens when we activate other cores, and again, these are tasks that are completely independent from the one under analysis. It's just running in parallel concurrently. So as we activate more and more tasks, you see the degradation in terms of the bandwidth that this application is able to extract. And you can see that basically we have a 8x slowdown on this one application that is memory intensive. And this happens, this is the trend that we see when the other cores are interfering with writes. So they're performing a lot of write backs in cache too. So what happens when instead the interference is made up of mostly reads instead? Well, not a lot of difference. I mean, yes, it's a little bit better because there's less pressure on the memory subsystems, but pretty much you see the same exact trend. And yes, maybe the slowdown here is, I think 4.5, 5x instead of 8, but you can see that this is not just a small overhead that you're potentially willing to pay, 10%, 20%, right? We are talking about significantly slower performance. So that whole distribution of execution time is shifting significantly to the right. Okay, so now we want to figure out where are the problems. And maybe here I'm going to also review some of the solutions that historically in my community we have worked on. So when we think about what are the issues that cause temporal interference, well, definitely the cores are typically not the problem. Sure enough, some folks have highlighted that coherence traffic between the cores could be a problem if you have applications that share a lot of memory. But pretty much the real problems, or at least the elephants in the room in terms of large sources of interference, happen at the level of shared memory hierarchy. Interconnect is typically over-provisioned. It's not too much of a problem. Again, this might change. You have seen some platforms that this starts to change. But fundamentally, the shared cache, the memory controller, typically the DRAM memory controller, and the DRAM storage itself are the big players where a lot of the interference occurs. And so if you want later, for some of you who are not familiar with this, for the reasons why this is the case, I may have some extra slides. We can go in the reason exactly why these are problematic. But again, coming from an historical perspective, what we have tried to do is essentially develop partitioning techniques. And here, software vendors are listening in, and it's increasingly more frequent that we see new solutions for resource partitioning. So, but again, coming from my history of works, this was back in 2013, where we started talking about how to partition, how to create a view of a cache which is shared into a logically partitioned cache, which is, for example, can be assigned to each core individually to lower the interference. And then we did the same thing at the level of DRAM. So with this, we developed techniques that essentially allow you to say, well, a core has access to a partition, a strictly private set of banks at the DRAM, and that lowers interference at that level. We also work on techniques to, for example, take the available bandwidth that is can be extracted in a way that does not saturate the memory controller, and then partition it between active cores, right? And so all of this set of techniques, again, we're talking about stuff that we worked on in 2015, 2016, so slightly old stuff now, but it's something that we call a framework of techniques that was called single core equivalent. So the ability to take a multi-core system and turn into an equivalent composition of single core machines, each of them that could be analyzed independently from the point of view of temporal behavior. And so since then, things have evolved quite a bit, also because support for virtualization, including in embedded systems, has become mainstream. And so the good old approach was saying, well, take your application, they can sit in different criticality domains, so things that are more or less important from the point of view of correct temporal behavior, and then take your OS, perhaps Linux, and evolve it into something that is SCE compliant, again, single core equivalence compliant. So on top of all the things an operating system needs to do, so for example, enforcing space isolation between criticality levels, now the OS also needs to be responsible for cache partitioning, for example, via coloring, or DRAM bank partitioning, or memory bandwidth partitioning, memory bandwidth regulation. Clearly, this doesn't work very well, because when you have multiple operating systems on the same machine, then you will have to re-implement all these techniques in each of them. And again, we believe that, well, at least we being the community, that techniques to perform partitioning should be beyond the scope of each individual OS. So a different take here has been into, well, rethinking the role of the OS, and somebody says, well, you don't actually need an OS at all. Perhaps you can get away with a unikernel if that's what you need per criticality level. Again, this can be debated. But then what's important is that actually partitioning can be performed by just a thin layer of partitioning hypervisor. And so, well, try to embrace this philosophy and have something that the community can use. We have taken the hypervisor jailhouse, which is something originally published by Siemens. So that's Siemens work. And we have taken it and added essentially a set of features that are extremely useful from a real-time perspective to try to enforce easy-to-use, versatile resource partitioning with the techniques that we have studied in the past. And so we created Jailhouse RT. Initially, actually, this started as a collaboration between BU and University of Reggio Emilia in Italy. And then this is now an effort that is much broader than a single institution. There is the TOM involved in Munich, University of Waterloo in Canada. Bosch folks working on the automotive system are seeing the importance of this. And then Minerva Sys is the latest essentially startup that is taking care of this piece of software and has promised to maintain it, upstream it as often as we can. I'm part of it, so I have some stake in that. All right, so we focus mostly on ARM64 machines, but these are not techniques that are, well, the implementation is definitely platform specific, but some of these techniques can be ported in different architectures. And if you want to access the code, it's now public, so you can follow this link. Perhaps somebody can put it on the chat if they want and access the source code of Jailhouse RT. What does Jailhouse RT introduces as sort of standard support? The ability to perform cache and DRAM partitioning via page coloring. The ability to perform, for example, dynamic recoloring, where we can reconfigure the way cache partitions are assigned even to the root cell. Root cell being the original Linux, like if you're familiar with Zen, that would be the DOM0 VM, right? And that also adds SMMU support to make sure that devices and CPUs have the same view of the colored memory. We also have DRAM bandwidth partitioning via performance counter, budget-based regulation. And we also support for ARM setting QoS regulators. So QoS regulators we will see them in a work that I'll present in a bit, but QoS regulators are extremely useful to regulate memory bandwidth consumed by hardware accelerators. And we also have some support for performing profiling. So if you want to acquire information of how CPUs, for example, are interacting with memory subsystem, we have special partitioning capabilities to acquire this kind of information. All right, so this is sort of stopping here with the advertisement of Jailhouse RT, but do feel free to ask questions on how things are done, or just look at the code if you want. All right, so the point I'm trying to make, and then we stop for some question, is that shared resource partitioning is a way to go. It's a powerful tool, okay, for which we need now well understood techniques, and that should be commodity for people to use and work with. But they are pretty much only a starting point as opposed to an end point. As I said, many hardware vendors are now introducing resource partitioning techniques in their hardware support. They're great. The problem is, as we will see in a second, that if you don't know how to use them, if you don't know how to configure them, partitioning can actually harm performance and timeliness instead of helping. So these are techniques that need to be commodity, and yet they are not the end of the journey.
So we actually have a question in chat, so I'm going to start with that. So it's from Pierre Pernetti, and he's asking, or they're asking, funny that we want systems to be context aware, and we never cared about threads of execution to be aware of each other. CPU schedulers are blissfully unaware about the mission criticality of the threads they schedule. Maybe if we put scheduling up the stack to the runtime level, we'd have more context aware control. Cloud systems like Cloudflare Workerd, which executes a massive number of operations in a single process, enables software control, context-aware preemption.
This is a fantastic point, right? The importance of embedding into scheduler decisions knowledge about our tasks, it is the way to go. The big problem, and this is what I'm going to be arguing and trying to evangelize you about, is that we fundamentally have always thought of scheduling as a problem at the CPU level, right? So our CPUs are programmable. We can schedule them. Maybe some accelerators now are programmable and we can preempt, for example, or define priorities at that level. But then everything under the hood is essentially out of our control in many ways. For example, you don't control exactly how the bus is scheduling memory coming from the CPUs. That's the main problem. Yes, fundamentally, it is a co-scheduling problem. The problem is that we have lost our ability to make the scheduling decision in an informed way at the lowest level of the hardware architecture, which is now our bottleneck in terms of performance. So our CPUs are not the bottleneck anymore. What's under the CPU, which is the whole memory hierarchy, is the bottleneck of our system. And we don't have the capability to understand how things interact with that subsystem, let alone collect information and retain this information and then act upon to adjust our scheduling accordingly. And not the scheduling of the CPU, the scheduling of the entire stack. And so, in fact, in this talk, what I want to show you is that if we embrace a new paradigm, which is that of CPU plus FPGA system, maybe we can recover some of that control, as we will see. You want to add some more, Ahmed, or are we good to go?
Actually, I have a contrasting question. So this question is about moving things up the stack.
Yeah.
Let me try to push things down the stack. So you've talked about, memory, being able to basically memory bottlenecks and how they are at different stages. So what about something like FPGAs to do all this stuff? Because, FPGAs have got these streaming pipelines where you can have data moving in and out without having to store this off chip. And if you have to store data on chip, you've got these block RAMs and a lot of them which could contribute to a virtually infinite bandwidth.
Yeah, this is a very good point. In fact, FPGAs are an extremely important transition in our computing models. And I personally believe, perhaps in a very biased way, that being able to push some functionalities down the stack into the hardware and then using the primitives that those can export at the higher level is really the way to go. So it's not one way or the other, everything at the high level or everything pushed into the FPGA, but it's really a cooperation of the two. Put into FPGA primitives that are useful and then leverage on those primitives at the high level of the stack to enforce more holistic scheduling decisions. So, okay, with this in mind, right, let's figure out why software partitioning is terrible, pretty much. Right? I said many good things about software partitioning, why we need it, but let's understand the drawback of this. So here, I'm going to just use Gelaw's RT to perform partitioning and a 4-core machine that has 4 ARM64 cores and 1 megabyte of LLC, lost level cache, and about 1.8 gigabytes per second of sustainable bandwidth. Again, this is a embedded system. And we run a image processing application called Disparity on a relatively small resolution. And then we observe its runtime. So this is the baseline. normalization baseline, so it's going to be 1. And this is when there is no jailhouse in the system, so nothing has been done. And then we turn on jailhouse, but we don't do any partitioning, so it's running alone, just with jailhouse under the hood to show that jailhouse is not adding a lot of overhead here. Okay, so what happens when we activate interference on the other cores and we don't perform any partitioning of LLC or memory bandwidth? So when we do that, essentially we notice a significant drop, degradation in performance. It's not huge, but 40%, we can argue it's a relatively important drop. And so what can we do? Well, what can we do is perhaps we can reserve 25% of the cache, 1/4, to this benchmark under analysis. And when we do that, actually we are not doing better, but the problems get exacerbated, and now our slowdown is even worse. So what we can do is try to increase it by 50%, by another 25%, so a total of 50% reservation for this one benchmark. And we do that, we still don't do better than not managing our resources at all. So we could increase it even farther and go to 75%. Now we start to see some improvement in the runtime of this application, but fundamentally we're still far from the solo case or the ideal case, the baseline. So what we could also do is now constrain all the other cores to consume up to 75% of the sustainable bandwidth. In this way, so while we have cache partitioning and memory bandwidth enforcement at the same time, then we start to see that perhaps performance become somewhat closer to our baseline. So again, partitioning techniques allow to have this control, but what's important here is why 25%, why 50% of the cache, why 75%, or why 75% of the memory bandwidth need to be constrained for the interference benchmarks. The point is we don't know, because fundamentally we have no clue of what this application wants to do. And this is the crucial point here. We need partitioning, but without knowledge of what the system wants to do, what the application wants to do, it's anybody's guess what is the right amount of partitioning that we need. And if we do it wrong, we harm performance instead of solving the problems in the first place. So we have been working on methods that can allow us to take applications that are black box and then try to analyze their behavior, right? And here I want to make an observation, right? So the typical goldfishness of our operating system manifests in just assumption that we have made about the way we handle, for example, memory. So typically we have an application, it has its own addressing space, and if you take an operating system like Linux, or I'm assuming Windows does the same, but it will take the entire application and say, well, this is normal memory, right? And it will map it to something called normal cacheable memory. But in practice, our platform are not one big block of memory, right? We are seeing that there is increasingly more heterogeneity in the type of memory technologies that are really in our system. Plus, there are certain ways in which manage resources that really change the temporal property of memory. For example, we could have non-volatile memory. We could have scratchpad, SRAM, and this goes on top of DRAM. Or we could have DRAM that is cacheable but in a shared cache partition versus cacheable in a private cache partition. And that changes the temporal behavior too. So ideally, what we would like to understand is the heterogeneity that exists in the use of memory in our application, and then be able to sort of solve this wedding problem between the heterogeneity on how much each page contributes to the timeliness of the application versus what is the temporal behavior of our memory technologies under the hood. And we are working on this problem, and indeed we started at least tackling the first problem, which is trying to understand how different memory pages are within an application addressing space. And so for this, we have devised essentially two methods that assume nothing about the application. For example, they don't assume that you can recompile it, or you can reverse engineer the source code. So I'm going to show you two methods very quickly. One based on some special hardware support in ARM system, which allows to snapshot essentially the content of the cache. And the other one, which is very platform agnostic, which is based on the fact that you can measure performance as you change policies for page allocation. And so the first method, very high level. If you want, take a look at this paper. I think it's interesting. Again, I'm bias alert there. But what we do is essentially we call it cache flow, and we use an NVIDIA Tegra TX1 platform. Let's look at disparity first, and we focus right now only on heap and an anonymous page, anonymous section is created when a big buffer is allocated on this application. And then on the x-axis, what we have is instance of time. So we perform snapshots as this application runs. And then on the y-axis, we have essentially the offset of the page inside the memory region, heap or anonymous region here. And we can construct essentially an heat map per each snapshot that tells us how many lines, how much of that page was actually found in cache at the time of snapshot. And so we can see essentially how the application is using memory as a by looking at it as a proxy of what we found in cache. And after every snapshot here, we reset the cache. So absolutely, this is not preserving the yeah, thank you. I see somebody likes the name cache flow. But this is not preserving the runtime. This is an offline technique, but allows you to understand exactly where the activity is on the pages of this application. And what's interesting is that if we do the same thing on a different application, for example, SIFT in this case, and now just look at the anonymous region, which is where the action happens, you can completely understand the difference in terms of memory pattern of how the working set size moves across these memory regions by, again, looking at what's being cached over time. This is the first method. It was published earlier this year. And then the second method, which was published last year, is even simpler. What we do is, we call it BBProf, so black box profiler, maybe not as creative as a name. But again, was implemented on an NXP IM6 quad platform. It's an ARM64 4-core machine. And let's stick again to disparity. And the only thing we do here is change the policy in which a page is allocated. Specifically, what we can do is saying, well, allocate everything as non-cacheable, right? And then run this application and measure its runtime. And then move one page from non-cacheable to cacheable. And then 2 pages from cacheable to from non-cacheable to cacheable, and so on and so forth. And what allows you to do, and then of course we sort them by their impact, but what allows you to do is to figure out the drop in performance, or rather the increase in performance. This is slow down on the y-axis, as you start moving pages from slow to fast zone, which means from non-cacheable really to cacheable here. And you can see that there is a set of pages that has a huge impact on the timeliness of this application. So once you set those pages to be protected, for example, in cache, or to be put on a fast piece of memory, then you can already decrease the runtime by 50%. And then there's another set of pages where you can reap the remaining, an extra 40% of runtime, and these are sort of mid-impact pages. And then there is normally a long tail of pages that actually, it doesn't really matter. They may be even non-cacheable, and it won't change a thing from the point of view of application runtime. These are pages that there's no point in consuming precious cache partition space, right, to make sure that these are allocated and preserved across runtime. So just to understand here that as we build methods to extract knowledge, now we have extra information if, for example, we want to change the allocation policy of pages at the operating system level. And again, this is not the end point, but I want to just make the point that we do need, and maybe I am just one drop in the ocean here, but we need better methods that can work across platform. It can allow us to easily profile a lot of the unknowns that is in how application use memory and how the use of certain pages impact their runtime. And we stop for questions here, right?
Just a really quick one, because in the interest of time, what is the output of these profilers? Like, do they just make recommendations, or are they able to dynamically change the program flow?
Yeah, a short answer is we're working on it. So right now, what they produce is essentially a profile that gives a ranking. For example, it says, third page of the heap is this much important. There's an index of importance. And then fifth page of the stack is this much important. And then by knowing the order of importance, you can essentially select how to allocate things. But right now, my students, as we speak, is working on how exactly doing that mapping, right? How to understand the performance of memory technologies, and then how to marry the two, right? Using profile information to correctly allocate things in memory. This is a very good question, right? All right, great. So here I want to show one example where, again, this is on traditional systems where profiling can really help in making informed decision on how we partition things, right? And here, instead of working on cache, let's talk about memory bandwidth. So here we have a system that looks like this. We have 4 cores divided into 2 clusters, each of them with their own LLC. And that means we don't have a lot of problem of contention at the level of shared cache, because only 2 cores share the same cache. And we can apply software-based regulation at the level of, at the entrance of these memory transactions into the shared interconnect, and therefore to memory. So we can set these quotas, right? So imagine this being knobs that you can set. And then what we have is accelerators. And because we have ARM QoS bus that allows you to throttle their behavior, we can also control, we can set equivalent knobs to control the bandwidth consumption of these accelerators too. So we have control on both, and we can now, we can now decide how things are composed. All right, so what else we have here? Well, what we did is, thanks to Jailhouse RT, we are able to take these 4 cores, and then for the purpose of offline evaluation, we can take one of them and turn into essentially a profiling subshell. All right, so what's interesting here is that we have 2 different memory controllers. So when we run our application and need to be profiled, we make sure that they access the first DRAM controller and the first block of DRAM. And we have our profiler on a separate block of DRAM to minimize interference. And then what we do is we have this profiler that essentially looks at a bunch of memory mapped performance counters on the DDR1. And as applications run, is able to sample it. So essentially is performing a polling of these registers and construct a very detailed profile at a microsecond accuracy inside its own piece of memory. So again, it's not interfering with the behavior of the DRAM by storing it on a separate piece of DRAM here with its own controller. And here we can show that we can go extremely fine grain, something like few microseconds of sampling period. All right, so with this in mind, what can we construct in terms of knowledge of our application? So on this platform, which is the NXP S32B234, just a generic ARM64 platform here, what we can observe is, for example, the bandwidth for the application under analysis, which in this case is region of interest, ROI. We can see exactly how the CPU is trying to access memory, at least its bandwidth, both in terms of reads and writes, blue and red curves in here. Then we can look at how the GPU is trying to access memory. Here, this benchmark is using both CPU and GPU. We can notice there is some other component in the system is consuming bandwidth. This is the display control unit, which is completely outside of the scope of this application, but nonetheless is putting extra load on our memory subsystem. And most importantly, we can evaluate from time to time how utilized, right, how close to the saturation level is our bottleneck, which is the DRAM controller here. And so we can plot really the utilization, which this approaches 100% when there's essentially a spike, a synchronized spike among multiple resources here. So with this information, what we can do is essentially come out with a memory profile of this benchmark. And really, this is not one line, it's really an envelope of possible behaviors across multiple, possible input vectors, but it's a profile nonetheless. And then we know that we have control over both CPU and accelerator bandwidth. And what we can actually come out with is a function. Again, I suggest you to read the paper if you're curious about how we derive this function. That really can predict, and we will see how accurately, can predict the runtime of this application, so the CI, given that we know what the memory profile looks like, and given that we know how the quotas were assigned to this application, both on the CPUs and on the accelerators. Not only that, but we can also calculate the impact, the worst case impact on the overall saturation of our memory subsystem from setting quotas in a certain way, regardless of what the software actually wants to do on the different accelerators and CPUs. So how precise is this estimate? Well, let's look at one of the results that we have on the same platform. Here we have all the cores active, plus the GPU is active on the benchmark under analysis, ROI. And here what we see is, the slope line is the predicted utilization, which of course is pessimistic. And then the vertical bar is the 100% saturation threshold. And the dotted red line here is the prediction on the runtime of our application under different level of regulation. Of course, as you give more budget, the runtime should decrease, as you can see on the x-axis. What is the actual behavior of the application? Well, the continuous line tells us the exact behavior of the application, which you can see is extremely close to the prediction until we hit saturation threshold, in which case, after which all bets are off, because the whole point of the regulation is to keep the system under saturation. So long as that's true, then we can easily predict in a very precise way what the runtime of the application is going to be. And this is the worst case, this continuous line. The average is somewhere in between. So this is the full envelope of all the runs that we did. Okay, so this is clear, I hope. So it really shines some insight on the fact that the real power comes when you have reliable and commodity partitioning solution combined with ways to understand the behavior of your workload, and then put the twos and twos together and create methods to drive system consolidation. Right? Sorry for the background noise. Right now I have there's some work right outside of my office. And I think here we can pause for a second for some questions.
I mean, I have one, but I think let's just keep going.
Okay, sounds good. All right, so what's next? Because so far we only said that we are using some data to statically partition, to statically set up the way we partition our resources. Can we do better? Well, all right, so here's where magic happens, because so far we've talked about essentially software-only management, knowing something about our hardware. But the problem is that this is great for partitioning, but rarely can go beyond and have something that is truly dynamic and adaptive at runtime. And even if you do, you have to be willing to pay high overheads if you want to go toward dynamic approaches. And the same for profiling. Typically, observing means impacting, a little bit of a Heisenberg non-determinism there. Therefore, we can only achieve a certain level of granularity before our overhead start going through the roof. And therefore, we have to be, both for management and profiling, we have to accept a certain level of granularity, which is typically coarse. On the other hand, we can say, okay, no, you know what? Your software approaches are too costly. Therefore, let's build better hardware that has, a brand new way of performing cache management. The problem with that is that whenever somebody comes out with a prototype, well, it's very hard to tell how they're going to behave in a realistic piece of hardware, because they're not going to go in production right away. And typically, they solve one problem, but they don't really see the big picture, and therefore, really, their programmability is limited because they're focused on solving one problem at a time. And even if everybody likes one solution, sometimes, researchers have to publish the next paper, so that strategy gets discontinued, in favor of the next big thing that we need to publish. And so as a result, we have many designs, many competing designs. It's unclear to see which one can actually make it to production. So is there a meet in between here? So perhaps we can achieve the best of both worlds if we have reprogrammable logic. And here I'm talking about the new, this new paradigm of computation, which is systems where you have hard pieces of computing facilities, for example, CPUs and GPUs and caches, why not? And you also have memory, traditional memory systems. But then in the middle, there is this large amount of reprogrammable hardware, FPGA, that can be configured as users see fit, or maybe system designers see fit. And these are not just, a utopia. These already exist, and you can go out and buy them, at least the one on the top. So UltraScale plus BiXilinx and recently AMD Xilinx, right, are probably leading the way in this type of technologies. But at the same time, we work with folks in ETH Zurich who are working on a massively larger system called the Enzian system, which has 48 cores and a huge block of FPGA. Is also cache coherent. So these systems are here to stay, because if you think about it, what they offer, and that's the killer application, is programmable specialization, right? So instead of having to set a production time on which kind of accelerators we want, just open that to the designer and allow them to define their own accelerators. But what's interesting, and this is what my research focuses on, is what are the other implications that really open up when you have hard and soft programmable logic on the same chip. And let me explore some of that with you. All right, so the first thing you can do is to understand that, well, typically, right, transactions that leave the CPUs directly go to DRAM. They follow, certain bus segment such that they cross into the DRAM controller and they're served there. But when you have a block of PL, programmable logic, what you really start to have is these very high performance ports that allow you to leave the PS and go into the PL, PS just processing system. And so what you could do instead is direct memory transaction to the PL, and then write a little bit of logic that allows you to loop them back in, such that when they enter back into the PS, they go in the same position in DRAM, access the same data, and then the transaction comes back through the same route. So what you now have is this little translator IP that just allows you to loop back these memory requests. Really becomes a place where you can write your own logic to program memory flows that are originated by application on the CPUs. So again, we're not trying to use this FPGA as an accelerator, but rather as a place where we can implement our own logic on how to manipulate memory flows. And this has extremely deep implications, I believe, and I will show you a quick train of results that we have been studying so far. So the first thing to understand is, let's put a name on things. So this strategy of looping things through the PL and back into the PS is something that we call programmable logic in the middle, or PLIM for short. And the idea is that essentially you have sort of client components that generate, sometimes people call them master components from a point of view of memory accesses, and then components that can reply to those requests. And what the PLIM approach says is, well, you can interpose logically a piece of PL, programmable logic, in the middle. And here, as flow of transaction comes through the PL, you can implement your own programmable logic. And so before we even go further and talk about the benefits of this, let's talk about the overhead, because of course, right, memory is a slow component and performance critical. So how much do we pay if we reroute absolutely everything? And here I'm talking about an entire OS and all the applications running on it through the PL. Well, here we have the color coded. The legacy route is going to be this color of bar, and then the new route PLIM that goes through the FPGA is this other color. And we look at some application, and again, put to one the baseline runtime. And these are, again, a bunch of vision applications, some of them more memory intensive than other, but overall memory intensive. And if we do absolutely everything through the PLIM route, then we pay for some of these applications a huge cost, right? For example, for MSER here, we are almost 50% slower. Notice here that, again, this is a rerouting of absolutely everything, but if you have listened so far, that is not the way to go, right? You want to reroute things depending on knowledge that you construct about your system. And the other thing you have to understand here is that the other route, the legacy route, is always available. So there are really two alternative routes to get to the same memory content that can be taken alternatively. And this needs to be done as you see fit, depending on the application. The important thing is that as you go through the PL, then you have a lot more control and observability, as opposed to not going through the PL. And that's really the big gain. And moreover, this performance drop can actually be improved. One recent paper that we'll present in December of this year actually shows that if you cleverly use coherence channels, you can bypass a lot of the slow interconnects and actually improve performance by just doing that. This is if you do for both reads and writes, and then if you only do for reads, because for example you care only about cache line refills, then you can actually further reduce the impact of going through the FPGA for absolutely everything, including the OS here. Okay, so with this in mind, right, what can you do, right? Now we pay a price, what do we gain? Well, a lot of things. So there are many things that we can manipulate now. We can change the semantic of addressing memory. We can change exactly how decisions are taken in terms of scheduling of this transaction to the memory controller. We can even change how data are taken from memory and passed to the CPUs, and we will see this in the relational memory work. And of course, we can observe and log metadata like OS level, core ID, source of where these transactions are coming from, type of transactions, cacheable versus non-cacheable versus memory barriers, and so on and so forth. So let's talk about the first work here. So in order to understand how this works, right, let's understand the role of the hypervisor in being able to go through the PL in a way that is pretty much transparent from the OS point of view. So here we can think about the OS and applications as essentially addressing a continuous range of intermediate physical addresses. And then typically what we have is a second stage translation. Here I'm using terminology from ARM64. If you have a naive translation, typically intermediate physical addresses translate directly into PA. Let's assume a linear mapping here between IPAs and physical addresses. So what you can do is, and typically these end up accessing a corresponding location in DRAM. What you can do is, if you have a PL, the PL is typically memory mapped. So what you can do is change at the level of second stage translation, the mapping of those IPAs into the range of the PL with appropriate offset to be able to translate back. And then here you have your translator that essentially changes back the address that the DRAM will see to rebase and access still the same content, albeit with a different route. And that I hope that this shines some light on how this translator works, which is just a manipulation on the addresses, really. So what does this enable, right? So what can we use this for? Well, essentially, it turns out we can use it to address some very long-standing issues with coloring and memory and cache partitioning in general. And let me explain that. So normally, when you perform coloring, you try to perform partitioning via cache coloring or page coloring. What you do is, well, you create a sort of restriction on the physical addresses, in this case IPA, intermediate physical addresses that can be associated to your cores, or more in general to your criticality domain. For example, here we have 3 criticality domains, and if we want to partition the cache accordingly so that the first criticality domain has 1/4 of the available space, then we assign 1 page to that, and then 1 page to, for example, the mid criticality, and then maybe 2 pages out of the total to the low criticality domain. And then essentially you keep repeating this pattern, and as a result, you have that the higher criticality domain will be able to access only 1/4 of the cache, the low criticality 2/4 of it, and so on and so forth. But what you do when you do this kind of coloring is you create an implicit coloring also of the pages in DRAM. So you create these holes on what you can allocate in actual DRAM, and this pattern follows the way you associated physical addresses or intermediate physical addresses to your applications. And so the problem is that essentially you're tying now the DRAM size to the partition size, which is not necessarily a desirable thing. And also, if you ever want to hope to recolor dynamically, you have to move a lot of data in DRAM now. So it becomes an extremely expensive operation. So what else we can do instead? Well, if we have CLIM, what we can do is insert a layer, an intermediate level of translation between addresses as seen by the LLC and the DRAM. And essentially, we can call this a cache bleacher, as opposed to, that undoes the work of cache coloring. And you still have your colored IPAs, but on their way from cache to DRAM, you can drop the color information and now have a nice cluster organization of data in DRAM, even though your cache is still partitioned. And the side effect of this is that now what you allocate, the amount of space you allocate in DRAM is completely uncoupled with the amount of cache that you allocate. Not only that, but now changing things, changing the way you assign those partitions is a very effortless operation, because all you have to do is change the mapping. Sure, you could set that aside and prepare it ahead of time. But then the data remains as it is. You just change the way the bleacher cancels out the effect of coloring in the translation. And I think we have a question here. Yeah, implementation of DPL. DPL is really a hardware module, right? DPL runs on the FPGA, which is a piece of silicon that is programmable and sits on the same die on chip and close to the CPUs. So we can do this efficiently. Yeah, so coloring though, this bleaching and coloring is done in the hypervisor in this case. So here the OS is completely unmodified. Right. Okay, so great. This is all nice and dandy, but the real question here is, so what? I mean, why we care about this? Here, I want to focus on two things, right? Which is, we've taken a technique that is fundamentally static, and because of the added programmability on the address semantics, we have turned this into a programmable solution that is amenable for dynamic partitioning. And now what we can do is, because we have dynamic partitioning, we can have that partitioning driven by information that comes from the profiler. But still, so what? Well, the real question here is what else we can do? We have opened a kind of worms here, and there's so many things that we can do at the level of reprogramming the semantics of memory operations. So one such example is what we call the scheme, the scheduler in the middle. And the scheduler in the middle is just a proof of concept of what could be done, which is, instead of sending CPU requests directly to memory, we can now create essentially per core queues on requests that are pending on the way to memory. And then what we can have is a programmable dispatcher, essentially a scheduler of memory transaction. And this scheduler can implement any custom policy, which we actually provide some templates for. We already implement TDMA, fixed priority, traffic shaper. But this is really opening the scheduler to programmability. So if the OS wants to deploy a new scheduling technique, it can. Moreover, this can work in tandem with now profiling information that can come from this traffic that we can finally observe and trace. So this is one thing. And let me show you just that how much control we have here. So we run all of this with the same application, same set of high intensity from memory point of view applications, and then we only change the scheduling strategy. And you can see that, for example, in fixed priority, the application, the core with the highest priority is essentially able to almost consume all the bandwidth, because the highest priority guy in the system. TDMA, you can see that they all go pretty much at the same rate with the slot system. That is not the most efficient, but the point is we can do it. And then traffic shaping, you can see that you can differentiate the rate of progress of the different applications as they go through memory. This trace, by the way, was acquired in the FPGA, so essentially it can be acquired by introducing zero overhead. And this is a recent project that we are working on, at least the first milestone has been already published. It's to appear in 2023. And it's the following. Here we play with the payloads that are passed between memory and CPU. So typically, when your CPU is accessing sparse data, think about a matrix stored by rows for which you only want to access the first column. Because of the way you store data, what happens is that when you try to access one element, because of the granularity in cache lines, you're now bringing in useful data, for example, the first item or the first column, but also a bunch of useless data into your cache, right? Which you will never going to use. It's going to be thrown away, but it still produces interference on all the rest of the system, all the other workloads. And moreover, changes the locality of the access pattern, right? So this is the traditional approach. What we can do instead is introduce a piece of PL that understands the geometry of data that the CPU is trying to access. This could be done explicitly, for example, by passing some metadata to the engine under the hood. And this is what we do for relational databases, where essentially the table schema allows you to figure out what is the exact geometry, for example, a table, a database table. And then it takes care of accessing in the most optimized way the memory under the hood. And what it does is it uses an internal buffer to reorganize the piece of data, stripping off all the useless information from the cache lines, and then always serve fully packed cache lines to the CPUs, in which case you're going to have always the first miss and then always hit on all the other fields containing the same cache line. Moreover, now prefetchers work really well, because from the point of view of the CPU, this is now a sequential access and not multidimensional stride access anymore. And so by just doing this, even if we pay the cost of going through the PL, we can improve performance compared to arranging everything via rows by 63%. And even if you store everything via columns, you can still do better by having this data reorganization in the middle by something like 87%. Of course, these are up to. Look at the full paper for details on when this happens and the full sort of spectrum of results, of course. All right, so what I want to convince you is that now that you have a new ally in your system, which is the FPGA, you can really delegate a lot of the observation and profiling and control low-level mechanisms, and then exploit those in your high-level software stack, the hypervisor or OS level. And let me just give you a peek into what I believe is the future here, which is now we are really able to construct extremely fine-grained, for example, space profile. What is a space profile? Well, something that tells you what's really hot at each point in time as the application runs from a point of view of space locality. But also at the same time, we can look at, and here we can isolate, for example, clusters of activity. And at the same time, we can look at how in time the demand of performance from the memory subsystem changes as the application progress evolves, right? And we can look at this sort of time varying profile of the demand of the application into the memory subsystem. And we could potentially define sort of stages instead of clusters of activity, stages in which we have, low bandwidth demand, high bandwidth demand, and anything in between. And when we do that, and actually this is currently a work in progress, we could potentially combine it with the fact that we can now live track the progress of our applications as they run in a way that is completely sort of zero overhead performing the FPGA. So this is what we are working on right now. We have a CPU that run a task, and then for this task, we know the memory profile. For example, we're profiling in advance using, for example, Plim. And then we have our PL, to which we now direct trace unit data. So you know that you have now trace unit, like in Intel, you have program trace. In ARM, you have core site. And you can direct trace data directly into the PL for stream processing. Here, we try not to store anything. We just stream process it. And then if we know our onions, right, if we know our tasks, we can create a per task tracker that uses this data to figure out where we're at with the progress in terms of stages in our tasks. And essentially we can deduce from this information which stages have been completed, which stages we are currently in, but most importantly, what's next in the behavior of this application or the expected behavior of the application. And that really allows us to plan ahead in terms of resource allocation, right? So the important thing that this allows us to add to our system is really knowledge-driven management, or AKA predictive QoS management. What I mean by that, what I mean is that you can have now multiple CPUs, each of them running a task and trying to access, for example, main memory here. For each of them, you can have a profile. For each of them, we can track where the progress is at. And then we combine this information, given the criticality level, the current demand, and the future demand of our application, and decide how exactly memory traffic is forwarded to the memory subsystem, be it a DRAM, be it SRAM, you name it, right? Or even off-chip memory, right? Or a remote socket memory, if you think about it. Okay, so with this in mind, we are approaching, I think, the end of my of my vision. And here, the last step in this approach in full self-awareness is really talking about software shaped platform, where essentially we can have this hardware components that help our software and are under our control, and really depending on the mission of the system, we can decide what components, what primitives we need to embed in our hardware and how to exploit them best at our level, at the highest level of our software, being applications, be OS, or be hypervisor. And so in the end, what I hope to have delivered here is that the steps of going from sort of where we are now toward self-awareness or knowledge-driven system management are the following. So first of all, first things I want to clarify or maybe stress one more time. Without proper primitives of management, essentially multi-core integration or a multi-core and accelerator integration is pretty much a nightmare from a temporal standpoint. And the first step in this transition is understanding that partitioning is needed, but it's not enough. Partitioning is pretty much poor man's management. Rather, what we need is shared resource management primitives that are well understood and can be used as a starting point. But on top of that, we need to have methods from which we can understand our applications and drive management accordingly. In the end, the end goal is not making one decision that can allow our system to operate from beginning of its lifespan to the end of its lifespan, because missions change. Rather, what we need is dynamic, informed system management. And this is my personal belief, but given that PSPL platforms are here to stay, I believe that they actually fundamentally change a lot of the assumption on what's really under our control and what is not. And in fact, they enable a new degree of observation and control and really new paradigms that can be developed targeting this programming paradigm, with this computing paradigm that, regardless of you want it or not, I think is here to stay, given that Intel has acquired Altera and AMD has acquired Xilinx nowadays. Last but not least, right? I believe that PSPL platforms really are the perfect playground, maybe not the endpoint, but perfect playground to test knowledge-driven system management strategies. And now, whether these are meant to stay in FPGA or transition inside our course long-term, this is, I believe, yet to be seen, but nonetheless allow us to perform a look ahead in what's coming next and what could be done in our platforms. Okay, with this, I just want to thank you for your attention. There is a few references here. This is this talk is being recorded, so this could be useful for people that are watching this being recorded. So this is my last slide. I just want to thank you for your participation and for your attention, and maybe we have some minutes for questions. You tell me.
Thank you so much, Renato. That was fantastic. Ahmed, do you have anything you'd like to say before I kind of wrap us up, or?
No, it's just a wonderful talk and a wonderful set of slides. And maybe just one quick comment. One of the things I really like about the FPGA work here is that, well, actually two things I like about it. One is where the FPGA is getting deployed, because when common argument is application development for FPGAs as massive overhead. But if you're doing it at the system level, for system level tasks, we can amortize those costs and we don't have to do it as frequently as application level. And the other thing I like is that we're preserving the legacy route, so that in the future, if you have an application that doesn't want the extra latency of going through the reconfigurable hardware, it can just take the legacy route.
Yes, indeed. Should I go through some of the questions that I'm seeing popping up on the chat?
I think we're getting tight on time. I don't know if you could handle any in like a minute or so, but what we could do is have folks reach out to you directly, if that's okay.
Absolutely.
That's perfect. Do you want to share? You have your contact information up there. So folks, if you're encouraged to email Renato directly with any questions, and we can always, kind of look at the chat as well and think about how we can address these in the project page. So with that, I just want to quickly share. Renato, can you take out your screen share off for just 1 second?
Absolutely.
Thank you. So huge thank you to Renato and to Ahmed for a really interesting talk today. This was really engaging and interesting, and I am excited that we recorded this so that you can later watch it at your own time if you were not able to see the whole thing or miss part of it. For some reason, I can't share my screen with the next event, but I will put a link into chat for our next talk, which is a November 16th from the Physics EU project. So you can actually link to that event now here and register. So please join us in November. And just again, thank you so much for joining today. Huge thank you to our speaker and to our conversation lead. And the recording will be up within the next few days. Take care, everybody.
Thank you so much for having me. And yes, indeed, I'll be happy to chat with anybody who wants to reach out.
Awesome. Thank you. Have a good day, everybody.